In this video, we're going to look at the discrete probability distribution, the geometric distribution. There are three main characteristics of a geometric experiment. There are one or more Bernoulli trials. What does this mean? This means you have a random experiment with exactly two possible outcomes, either a success or a failure, with all failures except the last one, which is a success. In other words, you keep repeating what you're doing until your first success. Then you stop. For example, you throw a dart at a bullseye until you hit the bullseye. The first time you hit the bullseye is a success, so you stop throwing the dart. It might take 6 tries until you hit the bullseye, or it could take more or less. You think of the trials as failure, 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 success. You hit the bullseye, then you stop. In theory, the number of trials could go on forever, but there must be at least one trial. The probability P of a success and the probability Q of a failure is the same for each trial, and the sum of P and Q is equal to 1. So Q equals 1 minus P. So the random variable is the number of independent trials until the first success. So, for example, the probability of rolling a 3 when you throw one fair die is 1/6. So a die has 6 sides. Each side has a number 1 through 6. If you roll one die, the probability of getting a 3 would be, well, how many outcomes are a 3? Well, there is only one outcome, that's a 3, out of 6 different possible outcomes. So the probability of rolling a 3 on a single roll of the die is 1/6. This is true no matter how many times you roll a die. Every time you roll it, the probability of getting a 3 is 1/6. So suppose you want to know the probability of getting the first 3 on the 5th roll. So on rolls 1 through 4, you do not get a face with a 3. You get some number other than 3. So the probability for each of these rolls is Q, 5/6, because there are 5 outcomes that are not a 3. That is the probability of a failure. So the probability of getting a 3 on the 5th roll is, so this is the probability that I don't get a 3, and 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 I get a 3. So we multiply these probabilities together. So it's the probability of not a 3, and not a 3, and not a 3, and not a 3, and a 3. So we multiply 5, 6 times 5, 6 times 5, 6 times 5, 6. Those are the probabilities that we don't get a 3 times the probability that we do get a 3, which is 1/6. So 4 failures, then a success. This is an example of a geometric experiment. You play a game of chance that you can either win or lose. There's no other possibilities. And you keep playing until you lose. And when you lose, you quit. The probability of losing is 0.57. What is the probability that it takes 5 games until you lose? So we're going to let our random variable x be the number of games you play until you lose. And this includes the losing game. So x can take on the values of 1, 2, 3. It could go on indefinitely. You could win forever, theoretically. So the probability question is, what's the probability that you finally lose on the 5th game? Well, the probability of losing is 0.57. So the probability of winning is 0.43. So the probability that x equals 5 is the probability that you lose, and you lose, and you lose, and you lose and you win. So we multiply the probabilities together because these are and type probabilities. So it's 0.43 times 0.43 times 0.43 times 0.43 times, you finally lose 0.57. And obviously, when you're playing a game of chance, losing is not necessarily successful. But in the concept of the geometric distribution, losing is a success because that's when you're going to stop. So the notation for the geometric distribution is as follows. We use a capital G to represent that it's a geometric probability distribution function. The random variable X is a geometric distribution, and the only parameter that the geometric distribution depends on is the probability of a success. An instructor feels, I don't know what that means, feels, that 15% of students get a below a C on the final exam. And I assume that her feeling comes from previous experience in giving a final exam. So she has been giving this exam a while, and she knows that 15% of the time students get a C or get a below a C, on their final. So she decides to look at final exams selected randomly and replaced in the pile after reading until she finds one that shows a grade below a C. So what we want to know is what is the probability that the instructor will have to examine at least 10 exams until she finds one with a grade C or below. So how do we state this particular probability mathematically? So what does it mean at least 10? So what does at least 10 mean? So that would mean what? 10 or 11 or 12 or 13 or 14. So at least 10 would be 10 or more. So this would be the probability that X takes on a value greater than or equal to 10. Now, how do we calculate this? Well, we need to go find the geometric distribution on our calculator. And if we're looking at the probability that X is greater than 10, remember from the binomial distribution, our calculator finds probabilities less than or equal to a value that our random variable takes on. So our calculator could find the probability that X is less than or equal to 10, but it can't find the probability that X is greater than or equal to 10. So if we want to calculate greater than or equal to 10, what we need to do is calculate less than or equal to 9. So this probability that X is greater than or equal to 10 would be 1 minus the probability that X is less than or equal to 9. So if we look at a discrete probability distribution, and discrete means that we can count the number of successes. If we look at this, then our calculator finds this. That's what our calculator finds. And what we're interested in is this. So if we look at the total probability being 1, to be able to find greater than or equal to 10, we must subtract less than or equal to 9 from 1. So this would be 1 minus the probability that X is less than or equal to 9. So let's go do that calculation. Sorry about that. That is not a calculator, that is. So here's our calculator. And again, our probability distributions are found in above the variables menu, which is right to the left of our clear. So we're going to go second distribution, and we're going to go find the geometric. So I'm thinking I'm going to find a distribution that's got geo. And there they are. So it's F and G. Went too far. Sorry about that. So F is the geometric PDF. So again, that's finding the distribution when the random variable takes on exactly a value. So exactly 9 or exactly 10. And what we're interested in is the geometric CDF. And what I really want to find is 1 minus the probability using the geometric distribution that x is less than or equal to 9. So I'm actually going to exit out of here. I'm going to quit, and I'm going to go back to my home screen, and I'm going to type 1 minus, and then I'm going to calculate that geometric distribution. So find my geometric CDF. And the only two values that I need to put in here is the probability of a success and what X value I'm interested in. So we had the probability of a success being 0.15. And we're interested in the probability that X is less than or equal to 9. And when we do this calculation, this is going to give us the probability that X is greater than or equal to 10. And that's 0.2316. Okay, for some reason that my animation's not too keen here. So we already see how to do this on the calculator before we actually talk about the problem. Let's talk about the problem. So assume that the probability of a defective computer component is 0.02. So 2% of the computer components are defective, which means 98% of them are not. Components are randomly selected. Find the probability that the first defect is caused by the 7th component tested. So this is a success. The first 6 trials are all failures because you're not finding the defective component. The 7th trial is the success because you're finding the defective component and you can remove that from the inventory. This is a good thing that you find the defective part and you don't put it in someone's computer. So how many components do you expect to test until one is found to be defective? So again, when we see this, what do you expect? This means we're going to have to find a mean, an expected value. So we are going to have to get a formula for the geometric distribution for the mean and the standard deviation. So this is geometric because you get a failure, 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 success. So it's geometric because the 7th component that I pick is going to be the one that's defective. So our random variable X would be the number of computer components tested until you find it effective. So this is a geometric distribution, and the probability of a success, the probability that a component is defective is 0.02. So our random variable could take on values of 1 or 2 or 3, etc. And we're looking for the probability that X equals 7. So in this case, we would not use geometric CDF. We would not use the cumulative distribution. We would use the exact distribution, We would use GeoMet PDF because we're interested in what's the probability that I pull exactly 7 components before I find one that's defective. And the probability can be found. Let's just run over there and do that real quick to demo how to find the geometric distribution, etc. So let's go to our calculator. So I'm going to go to my distribution menu and I'm going to find geometric PDF. The probability of finding a defective component was 0.02 and our X value was 7. We're going to paste that back into our home screen and we get 0.01772. Here is a graph of this particular geometric distribution, the y-axis containing the probability of X, where X is the number of computer components tested, the number of components that you would expect to test until you find the first defective one is the mean. The mean of a geometric distribution is found by 1 over p. So it's the reciprocal of the probability of a success. So in our case, mu is 1 over 0.02 or 50. So on average, you would expect to have to look at 50 components before you found one that was defective. The standard deviation of the geometric distribution is found by the square root of Q, the probability of a failure, divided by P squared. So since our probability of a success was 0.02, Q, the probability of a failure, would be 0.98. So we would take the square root of 0.98 divided by 0.02 squared, which is 49.5. Really got the animation on this one messed up. All right. So the lifetime risk of developing pancreatic cancer is about 1 in 78 or 1.28%. So let's let our random variable X be the number of people you ask until one says he or she has pancreatic cancer. So again, it's not a success that someone has the cancer. It's a success that you finally find someone who says that they do. X is a discrete random variable with a geometric distribution because it's geometric because you start sampling people and they say no, 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 yes. And when you finally find someone who says yes, you stop with your sampling. You don't ask the next person. For some reason, you're interested in finding someone who has pancreatic cancer for some reason. So X is a discrete random variable with a geometric distribution. X is geometric with the probability of a success or the probability of finding someone who has pancreatic cancer to be 1 over 78 or 0.0128. So what's the probability that you ask exactly 10 people before one of them says that they have pancreatic cancer? So this is the probability that X equals 10. So you would use the GeoMet PDF to find this probability, where the probability of success is 1 over 78, and you're looking at the random variable taking on the value of 10. So the probability would be 0.0114. What's the probability that you ask exactly 20 people before one says that they have pancreatic cancer? Well, this is again would be a geometric PDF, GeoMet PDF, where the probability of someone having cancer is again 0.0128. And now the random variable takes on the value of 20. So the probability is 0.01. The mean of a geometric probability distribution is found by 1 over the probability of a success. Since our probability of a success was 1 over 78, 1 divided by 1 over 78 is 78. So you would expect on average to have to ask 78 people before you found one that said they had pancreatic cancer. The standard deviation is found by taking the probability of a failure. So if the probability of a success is 1 over 78, the probability of a failure would be 77 over 78. So you take that number and divide it by the probability of a success, 1 over 78 squared, and you get about 77.49. And that is the end of section 4.4. The next video will cover sections 4.5 and 4.6 on the hypergeometric and the Poisson.